Hi, and welcome to my channel. My name is Philip, and this is ML with Philip. In this video, I want to break down and go step by step, teaching you how to build an RNN, Recurrent Neural Network, from scratch. We're going to walk through the code, and I'm going to break down the reasoning and the logic between each step so that we can build an RNN together piece by piece, and you can understand the entire process. This is part of a larger series where we're going to go through NLP, natural language processing, and we're going to learn how we can use machine learning and neural networks in order to solve problems in the English language, such as translation and text classification and more. In this specific video, we're going to walk through a notebook where we build a neural network, an RNN, in order to classify the language of a list of people's names. And this is going to be a character level RNN, which means that we process every letter in a person's name one by one, and we use that to finally generate an output which predicts which language that name belongs to. Before we get started and dig right into all of the theory and the code, I want to give credit to where I sourced the code for this tutorial. This comes from a tutorial on PyTorch's website done by Sean Robertson. That tutorial is called NLP from Scratch, Classifying Names with a Character Level RNN. I will link that in the video description and on the screen so that you can take a look. I didn't write any of this code. I rewrote some of the code for the purposes of this tutorial to make it clearer, to make it more like how I would write it. But all of the credit goes to Sean Robertson. And it was a great tutorial. It really inspired me to make this video. But the thing about that tutorial and other tutorials and resources that I've gone through on learning NLP and RNNs is that they didn't really show you the process of coding up the RNN itself. They gave you this code, which at many times is difficult to interpret because you're dealing with these multi-dimensional vectors. And that's always super confusing because it's hard to really visualize what's going on. I spent hours and hours really running every single line of code, looking at the output, reasoning things out, even drawing diagrams and doing matrix multiplication on pad and paper to understand what is actually going on. It would have been super helpful for me if somebody had made a video to just break down each of the steps and do like a code along to build the system together. Now, before we get into the coding and the actual meat and potatoes of it, I want to briefly introduce RNNs. Now, there's plenty of information and resources online on what an RNN is. I'll link some here, and I encourage you to really read up on the theory of it, but I will do my best to explain it. So, in a nutshell, an RNN is a type of neural network architecture which is used for sequences. So sequential data where there are time steps, and what the RNN does is it processes every step in the sequence one after the other. It basically takes an RNN cell and it takes in the input at each time step through the cell, And what it does is it outputs it produces an output, and that output gets passed back in to the RNN cell at the next time step. So what that does is it passes on information from previous time steps over to subsequent time steps. And this is super useful in natural language processing, because when we look at language, when we look at words, all of the meaning of the word or meaning in a sentence is encoded in the order that the letters appear. So for example, if we have the word apple, we recognize that to represent what we know as an apple. But if we were to slightly change the ordering of the letters, then it would no longer mean apple, it would mean something totally different. That's what an RNN is at a high level. Now I'm going to break down the structure of an RNN and draw some diagrams so that we can really get a better understanding of how an RNN looks like. Let's draw a little diagram here. So this is what we call our RNN cell. Okay, RNN cell. Okay, and this RNN, what it takes in is it takes in two inputs. Okay, it takes in one input, which is the input at the previous time step, t-1, and it takes in a hidden state, also coming from a previous time step. And what it does is it has two outputs. Okay, so it has and it has two outputs. It has an output and it has a hidden state. Okay, so what are all of these? Well, let's take an example. Let's say we have the word apple, and this is a sequence. And if we look at the time steps, well, this will be our time step at, we're going to start with the letter A. So we're already going to have the letter A. And let's say we want to predict the rest of the word. So this is going to be our first time step. It's going to be 0. It's going to be 1, 2, 3, and 4. But we have our RNN cell, right? And it's going to take in an input. And this is time step 1. So at time step 1, it's going to take in an input x0. And at time step 1, we take in the previous input, which is the letter A. So we're going to take in the letter A. And we're going to take in a hidden state. The hidden state is some information that the RNN cell has encoded from previous time steps that gets calculated and passed on to the next time step. So because this is our first time step, our hidden state is actually going to be initialized to just be a vector of all zeros. So this is actually going to be a 0 vector. And with these two inputs, we calculate an output. So our output that we're trying to calculate is we want to predict the next letter in this sequence. We want to predict the letter at time step 1, which is actually a P. But we don't know what the RNN cell will output. It might make a wrong prediction. It might output the letter B. We don't actually know what this will be, but we're hoping that it is a P. But it might be a B. So that's our output Y1. And we also compute a hidden state, H1. And this hidden state is some information that we've encoded from the character that we've just seen and any other previous information that we have that we want to pass along to the next time step, which is going to help the RNN cell predict the next character. So we've just processed the first time step, and now we copy this RNN cell and we pass the input at the next time step along to the RNN cell. So this is now t equals 2. Okay, so what do we take in? Well, we take in the previous input at x1, which is p. And we take in the previous hidden state. So h1 gets passed along here. And we predict the next output. So the next output that we would like to predict is p. However, we don't know what our prediction might actually be. Let's say we predict the letter x. We make another wrong prediction. Now, we might make a lot of wrong predictions at the beginning, but as we get more information, our predictions should be better. So, in any case, we make a prediction. Let's not use x because x is typically a variable. Let's say we use the letter e. Let's say we use the letter E. Okay, and we pass along information in the next hidden state. And we repeat this cell and we process the sequence one by one until we've gotten to the end. And usually at the end, there's a end of sentence token, a special token that indicates the end of the sentence. Actually, let's say in our case, this is just going to be a period to keep things simple. So this is 5. This is the end of the word. Okay, and that's essentially how an RNN works. Now let's dig into the inside of the RNN architecture to see how it's actually making calculations and predictions. Let us dig into the RNN cell itself and look at what goes on inside this cell. Okay, so as mentioned, we take in an input x at t minus 1, which is going to be a character. So let's say we have the character a. This gets encoded as a vector. So this might get encoded as a one-hot encoded vector that looks something like this. And we take in a hidden state, the previous time step. This is also going to be just a vector with some values, 1, 5, 7, -3, -6, whatever it may be. And what happens inside the RNN? Well, the first thing is that we take these two inputs and we combine them into one. So we concat h and x, and we create this new vector which has h in it and x in it. Okay, so we've combined these, we've just concatenated them into a single vector. Now what do we have? We have a linear layer here with a bunch of neurons. So what this linear layer does is it takes in the input, it calculates a hidden state. So we have a linear layer, and it is going to compute our hidden state. And then we have another linear layer here. And what it does is it computes, using the hidden state, this other linear layer is going to compute an output. So this linear layer is going to compute an output, which is also going to be some character. Let's say it's P. And so it might be 0, 0, 0, 1, 0, for example. And this hidden state T is also some new vector. And let's say it is, I don't know, 9, 10, minus 11, 0, whatever. Okay, so that's essentially what's going on behind the scenes in the most simple implementation of an RNN. And sorry, I missed one step here. So before we actually take the linear layer and then we compute a softmax. So I'm just going to add an intermediate step here. And so we actually take this linear layer and then we do softmax. Compute a softmax, and then we get a set of probabilities that gets converted into a prediction. So I just missed that step. So that's our system. And if I draw it in another way, we have input. We have an input. We have hidden at t minus 1. And these two go in and they get combined. And from that combined vector, we produce an output. And we produce a new hidden at time step t. And that's the basic structure. So this hidden gets passed back in here, and we do this again. So I will share these diagrams in the comments for you to take a look at and for you to review. But I hope that didn't confuse you more. I hope that explained the structure of an RNN. And now, with that understanding, let's go and start trying to build one of these. All right, let's dig into this problem and let's get started. The first thing we need to do is we need to understand the data that we have and the problem that we're trying to solve. So if you look at the data folder, which I will link in the description, and it will be on the GitHub repo, which is going to contain all of the source code for this tutorial. There is a names folder, and in this names folder, there is a bunch of text files, each containing names from a specific language. So the French.txt has French last names, the Italian.txt has Italian last names, and so on. And so we're just going to read in and do a little bit of processing on that data. I'm not going to go walk through this code because it's just reading in data. I don't want to waste your time going through that. So we just run all of this. We're going to get data that looks like this. We're going to get a dictionary, and the dictionary, the keys are going to be the languages. So the first key is Czech, and it's going to contain a list of Czech names. The next key, there's going to be a key for English, which is going to contain all the English last names. There's might be a key for Russian, and so on and so forth. Now, the first thing that we need to do in order to work with text data is neural networks understand data in numerical formats. So we need to encode this text data into a numerical representation. So the first step that we need to do to solve this problem is we need to encode data into numerical tensors. A tensor is simply a multi-dimensional array of data. So think matrices from linear algebra. Okay, so in order to do this, the first thing we need to do is we need to create a mapping from, and this mapping is going to map characters to indices. So what we're going to do is we're going to take all of our letters, and this was actually pre-computed here. So we're going to consider all of the ASCII letters plus some, punctuation spaces. So these are all of the letters that we're going to work with: A, B, C, D, E, F, G, so on, and capital case, and then some punctuation. So all we need to do is we need to take each of these letters and we need to map them to an index. So this is super simple. All we need to do is we need to go index to character is going to be, we're going to enumerate all of these letters, and we are going to convert them to a dictionary. Now, if we take a look at index to character, you can see that every single one of these letters has been assigned an index. Great. And we also want to have a mapping from characters back to indices. So we're just going to invert this dictionary. So we're going to do ji for I, j in items. Okay, and now we have a mapping from the characters to the indices. Perfect. So this is good. If we were to map a name using this mapping, we would get something like, say we want to map the name Philip. To get the encoding of Philip, now we would just do char to index of letter for letter in name, and this would be our encoded name, and what we would get is we would get this. So we would get 31, which is the index of F, 8, which is the index of I, and so on and so forth. Now, this is a numerical format. However, this isn't the best format for text data. The reason why is because we are assigning an ordering. So there's an inherent ordering to this data. So 31 is bigger than 8. 8 is closer to 11. So if we were to interpret this as a numerical data, then the machine learning model would understand that 8 and 11 are very similar to each other because they have almost the same value, but there's no similarity between different characters. There might be some small similarity, but it's definitely not represented by this ordering. So this would tell us that I and L are much more similar than F and F is different than the letters I and L. So we want a different encoding. So what we do is we actually one-hot encode each of these characters. So one-hot encoding is basically creating a vector of all zeros except for a 1 in the position of that character's index. So what is that going to mean? That means that for the letter F, it is going to, its index is 31. So if we were to one-hot encode it, we would have a bunch of zeros, 0, 0, 0, 0, so on. And then in the 31st index, we would have a 1. And then we would have a bunch of zeros again. And we have the number of characters in our vocabulary is equal to 57. So we would have, you know, a vector with 57 entries, all of them 0 except the 31st would be 1. And similarly, when we encode the letter I, we would have a vector of all zeros except the 8th entry would be 1. And that's what we want. Each character gets mapped to a 57 dimensional array. 1 by 57 dimensional array. And since we have 5 characters, this gives us a result of a 5 by 57 dimensional array. Okay, so when we encode our name Philip, we're going to have a 5 by 57 dimensional array. 5 because the length of the sequence is 5, 57 because the number of characters in our vocabulary is 57. So we want to start with that. So our tensor is going to be a tensor of all zeros, and it's going to have, its first dimension is going to be the length of the sequence, and the second dimension is going to be the length of our vocabulary. Great. And now all we need to do is for each character, we are going to need to set the index to be 1 at that character. So for each character in my name, I am going to take the tensor at, so we're going to take the tensor at the 0 position, and we're going to assign the 31st index. So we want the index of that character of F to be equal to 1. And let's see what results we get. Okay, so this is our tensor. We can see that in the first row, we have a one-hot encoding of the letter F. So it's going to be all zeros with a 1 at the 31st index. In the second row, we have a one-hot encoding of I. It's going to be 1 at the 8th index, and so on and so forth. And so this is going to be a 5 by 57 dimensional array. And now we're going to just call this the function name2tensor. It takes in a name and it computes a tensor. Okay, perfect. So if we were to do name2tensor of Alex, we get this. Amazing. So we've now been able to take our text data and encode it into a numerical representation. The next step is we want to actually define our neural network. So let's do that. Let's start with this. So we import torch.nn as nn, and we are going to call this class, we're going to call this class RNN, and we're going to define our constructor. So what do we need here? Well, first of all, we need to know the input size. We need to know the hidden size, and of course, we need to know the output size. So that's natural. I'll explain that further later on. And we need a forward method, which is going to compute, which is going to make a computation based on the input, and it is going to produce an output. Okay. For now, let's just return the input. Okay, so that's what we're going to start with. Very, very, very bare bones. And what we're going to do is we're going to have a test example that we're going to pass to this neural network. So our example is going to be, let's do name2tensor of my name, Philip. Now, let's initialize our RNN, and let's just go 0, 0, 0. And now let's try and compute a pass of this example through our RNN and see what happens. Okay, so we just return the input. Actually, because this is a character level RNN, we want to take the example at the first time step, and we want to pass that in rather than the entire sequence at once, right? Because the RNN processes everything one time step at a time. If you remember our diagram of our RNN, it takes in an input from the previous time step, but it also takes in a hidden state. And remember, during the first time step of the sequence, we don't have a hidden state, so we have to initialize it to 0. So let's set a hidden size. This is going to be the dimensionality of the hidden state. This can be set to really anything, but I'm going to set it to 128. Okay, don't worry about this too much for now. I'll explain further. And we want to initialize the hidden size because we're going to use it in our neural network. And so in addition to taking in the input, we're also going to take in the hidden state. Now, because we need to have a hidden state of zeros to start with, we're going to initialize the hidden state. So we're going to do this just for the first time step because we don't have a hidden state yet. And all we need for this is we just create a vector of zeros with the size of the hidden size that we used. So pretty straightforward. So this is our input, and our hidden state. So our input is equal to this. So our input is the encoded, the tensor encoding of our name Philip at the first time step, and we're going to, our hidden is going to be torch.zeros of n underscore hidden. And so our hidden state is going to be just a tensor of all zeros with 128, dimension of 128. So when we pass these through the RNN, we're going to pass in the input and the hidden. Now, we don't want to just return an input. We also want to, so let's do output is equal to input. And we're going to return our output, and we are also going to return the hidden state. Okay, so it's starting to come together. We want to use the information from the input, and we also want to use the information that we've been passed along from previous time steps in our hidden state. So in order to use both of those, we're actually going to combine the input and the output, the input and the hidden state together into a combined vector. So we're just going to concatenate the input and the hidden state. Perfect. And now, as we also mentioned in the diagram, we want to compute two things. We want to compute a hidden output, and we want to compute a prediction output. So what we do here is we need a linear layer that goes from our combined input and it produces an output, it produces a hidden state. So we're going to call this linear layer I to H, input to hidden, and it's going to be a linear layer, and its dimensionality is going to be the input size plus the hidden size, because that's the dimension of the combined input that we have, and its output is going to be the hidden size. And so now we're going to go hidden is equal to self.I2H of combined. Okay, so now we have the hidden. Let's set our output to just be the input for now, printing some of these shapes. So the input shape, the combined shape, the hidden shape, and we'll leave the output shape for now because we still need to compute that. Now that we have now that we're working with actual numbers, we want to supply the proper inputs. So our input size, if character has a dimension of 1 by 57, its dimension is n underscore vocab. Our hidden size is just n underscore hidden. And our output size is going to be, well, in this case, we're trying to predict which language a name belongs to. So we want to have probabilities for each language. So our output size is going to have to be the number of languages that we have. So lang underscore names is the data that we're working with. And these are all of the languages. So these are the languages. And the number of languages is just the length. So our output size is the number of languages. Okay, now this should work better. The input shape is just 57 because that's the one hot encoding of the previous character. The hidden input shape is going to be the size of the hidden size that we defined, 128. When we combine them, it's going to be 57 plus 128, 185. And then, of course, when we calculate our new hidden state, it's going to have to be the same dimensionality as our previous hidden state. It's going to have to be 128. And now our output, well, of course, it's going to have a dimensionality of the number of languages because that's what we're trying to predict. It's going to have a dimensionality of 18. Calculate our output is we just have another linear layer that goes from the hidden state to the output state. And of course, it's going to take in the hidden state, so it's going to have a dimensionality of hidden size, and it's going to have its output is going to have dimensionality of output size. So output is equal to self.h2o of the hidden. Okay. So our output shape is going to be that. Great. Now the thing is, when we pass the hidden through the linear layer to get the output, it's going to give us an output, of course, but we want this output to correspond to a prediction. So we want to convert these into probabilities. So we actually are going to do an additional step where we're going to pass the output through a softmax. Boom. So our output just gets passed through a softmax. And this doesn't change the dimensionality at all. Okay, so let's take a look at that. Okay, so we have an input size of 57, hidden size of 128, combined 185, hidden output 128, output shape of 18, and everything looks great. You can see that our output is a bunch of probabilities associated with the our confidence in each of these classes. So you can see that right now our RNN feels like pretty much all of the characters have the same probability. Our RNN believes that all of the languages have the same probability of this name belonging to them. And then this is our encoded information from the previous time step. Okay, and so what would happen is we would get the output and the hidden from the first time step. So this is time step 0. And we would actually pass those back in to get the output and the hidden for the next time step. Time step t equals 1. And we would keep doing this till we reach the end of the sequence. And I'm just going to remove these print statements now. So we have defined our neural network, and that's it. That was the main part of this exercise, was coming up with this neural network. And this is just me directly taking the diagram for the RNN that I drew previously and just putting it into code. Now that we have our RNN, let's train it. Boom. So the first thing is we need a loss function. We need a way of evaluating the
accuracy of our predictions. So what we want is we want the NN.NLLLLL, and the negative log likelihood loss is the way that we measure a penalty and a reward for when we get the right predictions and when we get the wrong prediction. It allows us to evaluate how well our neural network is doing and to perform gradient descent and iteratively converge on a better and better solution. The example that we used was the encoding of my name. And our latest output at the top was this. And now, if we take a look at the langs, my name actually doesn't fit into any of these languages. But let's say, for example, that my last name, or I passed in my first name. This is evaluating on last names. But let's say Philip was a last name, and let's say it was a French last name. Okay, so French is at index 7. So the true answer is 7. And this is our probabilities that our model has predicted. And we want to evaluate how well it predicted the answer. So based on what the probability assigned to index 7 is, 0, 1, 2, 3, 4, 5, 6, 7, it's negative 29.881, we can calculate our reward. So we do criterion of output, and in our case the target is 7, and we do this, and this is our loss. Okay, and of course we have to convert this to a tensor. So this will be torch.tensor, and now we calculate our criterion, and as you can see, the loss is 2.9811. For I in range of iters. So we're going to run this for, let's run it for 1,000 iterations. Okay, so for each iteration, the first thing we need to do is, with each new example, we have to initialize the hidden state. So the hidden state, remember, is all zeros, and we can actually just call this init hidden, which just returns a vector of zeros. So we can do this. Okay. So we want to initialize hidden state. And we want to reset the gradient, of course. And we want to get a random example. So let's write a function that fetches a random example. So okay, we have these languages and these names. So first thing we want to do is we want to sample a random language. So our language is equal to random.sample of langs. And we want to sample one language, and we want to take the first entry. Okay, so if we sample a random language, Spanish was the random language we sampled. Now within that language, we want to sample a random name. So we want to take the names at the language of Spanish, and we want to sample one random name from there. Okay, so the name that we sampled was Sierra, and we're going to sample it again, and the new name is Moles, last name. Okay, so let's just write this function, random example. We sample a language, we sample a name, and we return them. Okay, simple enough. Okay, so now we call this random example function, and we get a random name and its associated language. Okay, so we're looking good so far. Now, of course, we need to convert our name into a tensor, and we also need to convert our language into a tensor as well for when we evaluate the loss function. So if you remember, we have our name to tensor function. So our input becomes name to tensor of the name. Okay, and our target becomes, well, it just becomes this function here, torch.tensor of the language. And now we want to pass this input and this initial hidden state into our neural network, of course. So we pass in the input, we pass in the hidden. Oh, and yeah, as mentioned, we want to iterate through every time step of the input one at a time and pass that through the RNN. So actually we want to iterate through each for j in range, because we already used I up here, for j in range of the first dimension of the input, which is the number of letters in the name. We want to pass that through the RNN, and when we do, we're going to get an output, and we're going to get a new hidden state. Okay, so let me just recap what we've done so far. Initialize the hidden state, zeroed the gradient, fetched the random example, converted the input, the name, into a tensor, converted the output, the language, into a tensor, and now we pass the input through our RNN. However, we want to pass the input into the RNN one by one through each time step. So that's why we iterate through the first dimension. Okay. All right. Perfect. So now what we want to do is we want to calculate the loss. So we do criterion of the output, and we compare that to the target, and then we propagate the gradients all the way back, and we do back propagation, and that's it. So let's print I, and let's print the loss. Oh, and I almost forgot the most important step. We need to actually change our parameters according to the gradient so that we adjust them in the direction of decreased loss. So we need to actually adjust our parameters, of course. So for P and all of the parameters, we want to add the gradient to the gradient multiplied by the learning rate to each of the parameters, each of the weights in our RNN. Okay, and that is that. Let's take a look at what we get. Oops. Okay, and and the learning rate we need to set as well. Yeah, experimentally, I was able to figure out that this learning rate works well. But, of course, you can play around with different learning rates. Okay, we're going to need to reinitialize this RNN module because we didn't reinitialize it since we got rid of the print statements. So we'll run all of this code. And now we can see the loss. Okay, now the loss seems to be going down. It's hard to tell because we are calculating the loss for a single example at a time. So it's a little bit more difficult to see. So let's run this for a longer number of iterations. So 100,000. And let's calculate an average loss. And we'll calculate the average loss at at a checkpoint of 1,000. Okay. So if I is divisible by 1,000, then we will, so at each step we will add the loss to the average loss, and once we reach 1,000 iterations, we are going to divide it by the number of iterations, which is 1,000, and then we will print iterations I, and we will print the average loss and then we will reset the average loss. Okay, and we'll do item, and we are going to round this to 4 decimal places. And okay, I need to remove this print statement. Okay, let's see what happens now. Okay, so after 1,000 iterations, our loss is 2.8394. Okay, so we're definitely doing something wrong here. Okay, guys, I made one small mistake. And I realized that when the neural network was not actually learning. So let me correct that. So I actually need to specify the language rather than Spanish. And now let's try and run everything again. Sorry. And I added some extra print statements as I was debugging things. Now let's try and run everything again. Okay, and now we can see that the loss is going down, which is great. All right, guys, so one thing that I wanted to clear up, because I understand this might be confusing, is that when we went through the diagram for how an RNN worked, we were talking about it in the context of a sequence generation, character generation problem, where we're trying to predict the next letter in a word. In the problem that we just went through, we're actually trying to predict the language associated with a name. So in this problem, the output might look a little bit differently. So I just wanted to draw a diagram to explain what the output might look like in this scenario. So similarly, we still have our RNN cells, but now at each time step, we have, for example, the last name Smith, S-M, okay, the last name Smith, and we have time step 0, 1, 2, 3, and 4. Okay. At the first time step, we get our hidden state H T minus 1. Okay. We get our input. So at time step 0, at t equals 0, our input is the letter S. Okay. And I'll just put this out of the way. T equals 0. We get an input of the letter S. Now our output is not going to be the letter M, because for this problem, we're trying to predict the language associated with this name. So our output is going to be a language. And let's say with just the letter S, maybe there's a lot of Spanish last names that start with the letter S. Our output might actually is going to be the language that we're predicting, and it's going to be Spanish. Of course, the output is going to get better as it sees more time steps in the sequence. So it might be Spanish. The target is English. Okay, and then we go along to the next time step, and now we take in the letter M. And we perform a prediction. So SM, let's say the Czech language has a lot of last names that start with the letters SM. So we predict that this is a Czech last name. Okay, and we keep making these predictions, and it's only until we get to the very end and we take in the letter H, when we've seen the entire word, that we will output our final prediction. And this will be our best prediction. And let's say the final prediction is, once we've seen the entire name, we're actually able to correctly predict the language to be English. And this hidden state no longer matters. Okay. So the difference here is that instead of predicting the next character in the sequence, it's predicting the language based on the characters that it's seen. And then this is our final output that we evaluate against our target. Is this equal to question mark? Is this equal to our target of English? Yes. And so that's how the RNN cell works in this context. Just wanted to clear that up in case that was confusing to anybody. Okay, at this point, we've created the RNN. we've trained it, and now let's take a look at using our RNN to make some predictions now that it's trained. And let's see how well it does. So, how do we make a prediction? Well, we made a prediction here when we set up the training loop. But let's do evaluating on some inputs. So let's copy some of that code. So we take, this is how we were generating an input and an output. We were taking the language and the name from a random example, and we were just passing it into the RNN through all of the time steps, and we were taking the final output. Okay, so the final output gives us a bunch of probabilities, right? Now, we want to take the biggest probability in this, in these log probabilities. So what we can use is we can use this function called top_k. Let me just check the top_k. And what that does is going to select the top probabilities. So we're going to select the top 3 probabilities. And let me just remind myself what this function does. Okay, and along the first dimension, and we want sorted. Okay, so if you look at our output, so the top 3 probabilities, remember, these are log probabilities. So when we, convert them back into e to the exponent of, the smallest ones become the biggest probabilities. So our top probabilities are at index 0, at index 10, and at index 8. Okay, so these are our top k predictions. And let's see which languages those correspond to. Well, top language predictions. Well, we can just take the langs at the index of that top k. So top underscore k. Okay, we want the indices. So this is top k at 1. Okay. Sorry, langs at that index. Okay. Okay. So the top 3 languages that were predicted were Czech, Spanish, and Irish. Okay, this was for a random example. Now let's say we want to use our own example instead of a random example. So let's now, instead of lang and name, we are going to specify our own language. So let's use the language of English, and we'll use the name of Smith, and let's run the code again. Our top k predictions. Okay, the top 3 predictions were Dutch, Scottish, and German. So maybe English was not an actual, oh, it was, okay. So I guess Smith is predicted to be a Dutch last name, although it is an English last name. So our model didn't do that great on this last name. Let's do something something different. Let's do something like Chang and Chinese. And let's see. Okay, and it predicted it to be Korean. So maybe I'm wrong and Chang is actually a Korean last name. But you get the idea. Okay. So let's wrap this in a function. And let's just do some random evaluations to see how well we were actually able to do. So the predict function is going to take in a name and it's going to take in a number of predictions. We'll default to 3. And we're going to wrap this in torch.nograd because we don't need to do backpropagation and keep track of gradients here. So let's go ahead and copy all of this code. Okay, we don't need the language and we don't need the target. We do need this. And we do need this. And we need this. Okay. So now if we call predict on the name Chang, oh, we need to initialize the, okay, probably why we were getting bad predictions before is because we didn't initialize the hidden state before we did these predictions. So let's fix that now. Sorry for missing that earlier. That is totally my mistake. So the reason we had some bad predictions before is because I was using a hidden state from a previous output rather than reinitializing it. So now that I fixed that, okay, we're still getting Chang, we're still getting Korean, so maybe Chang is a Korean last name. Let's see what we get with Smith. Okay, now we get German, Scottish, English. Well, you know, our model obviously leaves a lot to be desired. It's a very simple implementation of an RNN. It's going to get much more sophisticated going forward, so don't worry about it too much. Okay, so let's do some predictions and see what we get. So let's do 10 random predictions. So we're going to get some random examples and we're going to predict and then we're just going to print everything out. Okay, so for example, when passed in the last name Meindl, it predicted it to be Irish, but it was actually German. when passing in the last name Cavalcante, it predicted it to be French when it was actually Italian. When passing in the last name Rivero, it correctly predicted it as Spanish. Passing in the last name Colbert, it predicted it as Dutch, but it was actually Czech. And you can go down the list and see more. So, of course, some of these languages have overlapping last names. So you can expect that some of these predictions will be difficult to get the exact right language. There could be more than one right answer. All right, amazing. So let's actually plot a confusion matrix which shows us for each language which prediction is our model likely to make. So I'm going to create a confusion matrix here. And I'll explain what this is as we code it along. So first of all, it's going to be a matrix where the rows are the languages and the columns are also the languages. And the rows are going to be, the language, and the columns are going to be the predictions that we made for that language. So let's start with an empty matrix. And we're going to perform 10,000 random predictions. Okay, so we're going to simulate this model 10,000 times. Ooh, my back's hurting from sitting all day in this chair. But I wanted to get this video done so that you guys can learn and I can share my machine learning knowledge with you guys. In any case, let's continue. So we get a random example. And now we are going to perform a prediction. And we're going to take our top prediction and we're going to get the index of that language. Okay, and we're going to do the same for the target. So this is the ground truth, and this is our prediction. And then on the confusion matrix, in the row for whatever the actual language is, we're going to add 1 to the column of the language that we predicted. So in this confusion matrix, we keep track of the true language and the predicted language. Okay? And so, did I do something wrong here? Apparently I did. Okay, sorry. We meant to use our target, which is the index of the language instead of the language. Okay, so yeah, so now we will let that run, and then let's take a look at our confusion matrix. Okay, so it's not stacked up nicely, but let me take the first 5 columns. Okay, so what this means is that for the first language, which is for the Czech language, we correctly classified, for the Czech language, we predicted 247 of them to be Czech. We predicted 26 of them to be German, 2 of them to be Arabic, 12 of them to be Japanese, and so on. For the German language, we predicted 38 of them to be Czech, 151 of them to be German, and so on and so forth. Now, we're just going to normalize these. So let's do that. And now I'm going to copy some plotting code. Okay, so here's our confusion matrix. And you can see that from here, you can see that Czech is most often mistakenly predicted as Russian, French, Dutch, or Polish. German is most often mistakenly predicted as Dutch. Makes sense. Chinese is most often mistakenly predicted as Korean and Vietnamese. That makes sense as well. Spanish, Portuguese, Italian, that all seems to line up with our expectations. Now, one more thing that I wanted to do is I also wanted to plot our learning curve. So what I'm going to do is I'm going to go back to our training, and I'm going to save all of the losses in a list. So I'm going to append the iteration, and I'm going to append the average loss. So I'm just going to save all of these in a list. Okay, I'm going to run this again, and I'm going to plot the learning curve. All right, guys, so I just wanted to go through one last thing, which is to take a look at the learning curve for our training. So what I've done is I've plotted all of the average losses after, at intervals of 1,000. And I just wanted to examine this graph. So we can see that we start off at a loss of around 2.8, and we very quickly start dipping down, and the loss steadily decreases, and it starts to plateau around the 1.3, 1.4 mark. And that's typical of neural networks and machine learning problems that you learn really fast at the beginning, and then your loss starts to kind of level out and it stops learning as much. And once that happens, you probably want to start decreasing your learning rate. But from this loss curve, we can see that our model did a very good job of learning how to predict the language of different last names. So this is the end of the core part of the video. If you followed through the entire video, then thank you so much. I hope this was useful to you. I hope that you learned, and please leave any feedback in the comments. I'm going to do a quick recap of everything that we've went through. So let's start at the very top. We read in the data, and the data that we had was a bunch of text files with names in different languages. And our task was to design a neural network to predict the language that last name came from. So the first thing that we had to do is we had to encode all of our words and our text information into numerical information that could be processed by our neural network. So we did that by defining an index for each character, and then one hot encoding all of the characters, and then taking all of those encoded characters for the entire word and putting it into a matrix. Then we defined a neural network. And we defined a recurrent neural network according to the architecture that we went through earlier in the video. And what this recurrent neural network does is it produces a prediction at every time step, and it produces a hidden output at every time step, and that hidden output gets taken in as input into the next time step, so it's able to pass along information across time steps in the sequence and incorporate that into its calculations, into its predictions for the current time step. The next thing we did is we wrote a training loop in order to make predictions, calculate the loss, and then do back propagation, find our gradients, and adjust all of our parameters so that we could iteratively increment our weights to get closer to a more accurate model. And we did that for 100,000 iterations. And we got these loss curves, which showed how our neural network was able to learn. And then what we did is we just generated a bunch of predictions to see how our neural network is performing. And we could see what kind of mistakes it was making and which languages it was correctly classifying. So we also took a look at a confusion matrix, which again shows us which mistakes the neural network is likely to make. So that was the tutorial. That's everything that I wanted to cover. That's the core of what we wanted to achieve today. Build the most simple RNN that we could, apply it to an NLP problem, and look at the results. But there is some extra optional material that I'm going to go through in a second video. And in that video, we're actually going to replace our implementation of an RNN from scratch with PyTorch's pre-built RNN function. And on top of that, we're going to try and experiment with using a GRU, which is a more advanced, sophisticated version of an RNN. And we'll even take a look at using an LSTM, which is even more sophisticated. So that will be in the additional extra video. So take a look at that. I'll link it in the description if you're interested.
You've reached the end of the video. Thank you so much for watching, and if you made it all the way to the end, leave a comment down below letting me know. I know this was a super long video. If you felt like you got something out of this video, then please leave a like. Check out my channel for more interesting machine learning tutorials and videos. I will leave a link at the end of this video with the rest of the series, as well as the video to part 2, where we dive deeper into PyTorch's RNN implementations. Thanks for watching, and I'll see you next time.